to things like web servers rather than people. So between Alice and a web server, in this case Bob is a web server, a interactive bidirectional link is set up. Okay? So it's not just that a message is sent and then something sent there and something sent there and on, but rather a real-time interactive nested encryption tunnel is set up that allows packets to travel in approximately real time through the internet, being decrypted, nested decrypted one way and nested encrypted the other way. Okay? And this is great for real-time requirements like World Wide Web and instant messaging and stuff like that, right? It would be bad if when you fetched a web page, it took like an hour to come down. Or if you're having an IM chat with someone and it takes an hour for each message to get there, or worse, a day, right? That would be ridiculous. That said, in the early days of the web, there were systems before like most people had computers. There were systems that would allow you, this is a digression, but it's funny, so. There were systems that you would, they would fax you a web page, and next to every hyperlink there would be one of those little mark circles like you take on exams, and you'd mark the ones you were interested in clicking and you'd fax it back to them. And then they would fax you the pages that result from clicking those links and so on. So, and this was all automated. So that's about as high latency as you want, as you can deal with for web traffic. So Tor handles it quicker than that. On the other hand, what do mixes do? In a mix, each mix node collects the messages that are sent to it and then holds on to it and waits for some amount of time or for some condition to hold. And we'll talk a little bit more about this in a bit. But it holds on, gathers a bunch of messages together, and then opens up all the envelopes, shuffles them into a random order, and sends them on. And that shuffling is what we call mixing. And the goal of the mix node is to prevent someone who's watching the network from being able to see, oh, these messages came into the mix node, and these messages came out, and being able to figure out which incoming message corresponded to which outgoing message. Okay? So that's the job of the mix, and that's something we'll spend most of our time on today. How does the mix make sure that you can't link incoming messages to outgoing messages? But because it's holding on to messages for some amount of time, you can't use it for real-time traffic, like World Wide Web or instant messaging, but you can still use it for traffic that's not so time-sensitive. Things like email, and things like blogging, and things more recently like microblogging, like Twitter, right? It's not so vital that your tweets make it online right now if what you're doing is you're tweeting about what's going on the ground in Iran during the protests, right? It's okay if it's delayed by an hour or so, or even a day, as long as the message comes out and they can't identify that you're the one that sent it. Okay? So, mixed networks have two major pieces. The first piece is what I mentioned just a bit ago, the mixing strategy. So as messages arrive at a mix node, how does the node determine how long to wait before processing it? Okay? So some simple mixing strategies are wait until you get 100 messages, then process them and send them all on. Or wait for an hour, and however many messages you get in this hour, you process them and send them on. Or you can do something called a pool mix, which is wait until you have 100 messages, then pick a random 50 of them and send those on, and the other 50 just wait in the pool until you get 50 more, bringing you up to 100, and then you select a random 50 and send them on. Okay? That turns out to have a lot of nice features. There are lots of different mixing strategies. Some of them allow the user to communicate some preference. For example, you might want to tag a message with, this message is really needs to be really secure, and I don't care if you hold on to it for extra time if you think it'll add security. Or the user might tag the message with the opposite, saying, put this through as quickly as you can, my privacy is a little bit important, but not so important. Okay? And that those parameters to the mixing strategy will come back later on in the talk. So just remember that there are lots of different mixing strategies, and many of them have certain parameters that the user can communicate. Okay? Other than that, I'm not going to talk more about mixing strategies in this talk. This talk is about the other attribute of a mixed network, the mixed format. Okay? So, as I said, there are lots of mixing strategies out there, all with their pros and cons. The other half is the mixed format. The mixed format is the sort of the byte-level description of the mixed message. Exactly what do you encrypt? Exactly what fields do you put in your message? How big is the message? Right? And the important property of the mixed format is that it's exactly what keeps an attacker from linking up the incoming messages to the outgoing messages. Okay? For example, take a really naive mixed format where all you do is you take the message and you just public key encrypt it 3 times. Okay? There are several things wrong with this. First of all, what about messages of different sizes? So a small message comes in, and a medium-sized message comes in, and a large message comes in. And a small message comes out, and a large message comes out, and a medium-sized message comes out. Well, it's pretty obvious which one was which, right? So the mixed format has to hide the lengths of messages. That's one of its jobs. Another one of its jobs is to hide where you are in the path. So for example, if you, again, just did that naive thing, even if you insisted all messages were of constant length, you would have the problem that every time you did a public key encryption, the message would get a little longer, because public key encryption adds some overhead. Okay? So the message would get a little bit longer. So by looking at the size of the message, you'd know where in the path you were. In our envelopes example, if we were to do this in real life with real envelopes, of course, each envelope that you nest inside would have to be a little smaller than the one on the outside. So if I hand you an envelope, you can just measure it and say, oh, this is the 3rd envelope in the sequence. And that's also something we'd like to hide. So things like the length of the path, the position in the path, the next node in the path, and so on. These are all things we'd like to hide. Okay? The mixed format also determines another important property, which is whether Bob can reply to Alice. Okay? Remember how I talked about the anon 25549? That was a mechanism for replies. And it's important that it's at least very useful that a mixed network support the ability for people who receive messages to reply to them. Okay? Otherwise, it's kind of tough to have communication. It's all one way just shouting, right? And no one can have a conversation. So being able to reply to a message that was delivered anonymously so you don't know who it is, who sent it, is quite a useful feature. Now, even if you support replies, it's important for security. It turns out that what you want is that the reply message should look just like any other message in the system, the so-called forward messages. And the reason for this has to do with a concept called the anonymity set. And the anonymity set is basically the number of people using the system or that could have sent this message. So imagine an anonymity system like a mixed network or like Tor where only 10 people in the world use it. Okay? Then if a report out of Iran came from this anonymity system, well, you know who sent it. Well, it's one of these 10 people. Oh, only that one lives in Iran. Well, it didn't provide you much privacy at all. Right? So the more people that use a system, the larger the anonymity set and the better the system protects you. Now, if forward messages and reply messages are handled differently, so if the node, when it's processing a reply message, has to do something different from when it processes a forward message, then basically the forward messages and the reply messages are going through essentially 2 different networks. It's easy for the adversary to just distinguish the forward messages and the reply messages, and now each network only has half as many messages going